Hi, in this video, we want to take a look at analyzing categorical data statistically. All right, so we're going to take the PowerPoint slides from Rosner's Essentials in Biostatistics textbook, and we're going to go over several tests. All right, just to let you know, I'm professionally a data scientist. I am not, teaching is only a side gig for me. And professionally at work, I use these techniques every single week. This is a huge part of my work, is to use categorical data analysis. I typically use the chi-squared test the most, so that's one that I'll probably say the most about. But all of these are good, all of these are solid. If you want to have a full set of tools in your tool belt, you need all of these. So what we're going to go over a binomial version of categorical testing. Then we're going to talk about chi-squared tests, where here this is going to be like a table of numbers, a rectangular table of numbers, and we want to make statistical inference off of them. We're also going to talk about 2x2 contingency tables. The chi-squared test can handle 2x2 or larger tables, or even just a 1x2, 1x2, 1x3, something like that, 1x20. We'll talk about Fisher's exact test and McNabar's test for correlated proportions. Now, all of these handle similar problems in a slightly different manner. What the chi-square test does is it takes an expected value and compares the results that we have to the expected value to see if we have something going on, something interesting. Fisher's exact test, what it does, it says, hey, if I moved around the points so that I still had the same row sums and the same column sums, same number of observations as each row and each column, would I get something that's very different than what I observe? And then McNabar's test looks at like a correlation aspect. So like with the 2x2 tables, it will be looking at the diagonal versus off diagonal entries. So let's go ahead and scroll up to the beginning. All right, so we're doing hypothesis testing on categorical data. All right, so what we want to do specifically for this presentation is we're concerned with two possibilities: yes, no, true, false, success, failure, something like that. And we want to analyze those proportions. And we only have two possible outcomes that we're considering for this moment. All right, so it might be that we have a belief of what the distribution is. And in that case, we're going to be doing a goodness of fit test. Typically, we will be using the chi-square test for this. All right, so the first one we're going to talk about is the two-sample test for binomial proportions. All right, so what we're going to do is I'm going to treat the proportion as being connected to the normal distribution. So what's going to happen is that I'm going to assume that what I have from my binomial distribution is, if I take the number of successes I have, I can divide by the number of possible, number of opportunities for success, divide that, and that gives me a proportion. I can look at that as being an average, because if I put a 0 for failure, 1 for success, then that is a sample average. It's a sample average. Therefore, more than likely, I can apply the central limit theorem. Therefore, I can use the normal distribution. Okay, so what we want to know is, do we have the same proportions for two populations? So I have two different populations, and I want to know, do these have the same proportions overall, or are they different? Or we can also test if one is greater than the other, one is lesser than the other. We all, two-sided or one-sided tests. All right, so if I'm using the normal distribution, so here I'm using the central limit theorem approach to this. So the central limit theorem says if I'm taking an average under most situations we see in real life, then the average or the difference of averages will be approximately normally distributed. Therefore, I can use the normal distribution to get my p-value. And once I get my p-value, I can reach a conclusion. And so here, this will be my test statistic. So this is the observed proportion in the first population, observed proportion of successes in the second population. If I'm trying to see, are they equal to each other, or one's greater than the other, one's less than the other, I'm going to subtract them from each other. And this will be approximately normally distributed under some mild assumptions, assuming I have a large enough sample size in each population. And so then, to get my test statistic, what I need to do is I need to divide by what is the standard deviation of this particular number. So we call it standard error. We call the standard deviation of a statistic the standard error. So we will divide by the standard error, and this will be approximately normally distributed. Once it's normally distributed, then I know exactly what the population distribution should be. I can reach a conclusion using hypothesis testing. Now, something that we can do is we can go ahead and get the overall success rate. And so this is for the entire sample, assuming that there is no difference between these two guys. So under the null hypothesis, these are equal to each other. The P1 hat, P2 hat. So if P1 is equal to P2, then my best approximation of the overall proportion is to just go ahead and take all the successes divided by all the opportunities for success. And then we see that here in the P. Now this Q is 1 minus P. In statistics, we represent Q for 1 minus P because it comes up so often to just give us a little bit of less to write out. We write Q. We're just being lazy. All right, so here we're using the normal distribution. Here is our test statistic. Now, what's going on here with this part? If my sample size is not excessively big, it can work out that things don't work out exactly the way we want it to in terms of those cutoffs. So because I have discrete numbers and I'm approximating the distribution with a continuous distribution, there's kind of a mismatch there. And so what we're doing here is this subtraction is a correction term to give us a little bit better performance in the test. Now you'll notice that if I have large sample size, it really doesn't matter because, you know, if I divide by something big, I get something small. And so large sample size, it won't be an issue. It's an issue when I have smaller sample size. And so one thing about this is when we go through this, when do I have enough samples for this? Well, here's the one criteria. Different textbooks will change these numbers slightly, but 5 is pretty typical for a lot of people, that we want for each population that we're sampling from, we want the number of observations times the overall success rate times the overall failure rate needs to be greater than or equal to 5. And that needs to be, this multiplication needs to hold for both of these, both populations that we're working with. If this doesn't work out, if this is equal or less than 5, then my sample size is too small considering the observed variance in the data. And so we can't really trust the test using the normal distribution because there's too much going on, too much spread from this term and not enough sample size to compensate for that spread. So in that situation, we would need to do manual calculations with a binomial distribution. And in R, if you do the binomial test, that will automatically run the binomial distribution for you. If I want to use the normal distribution, I want to use prop.test. Now, overall, almost every single time that every time I've ran this, the results end up being close. Now, if it's close to the cutoff, close to the borderline, you know, there might be different. In general, the exact test will be better, so the binomial distribution is a better one to use. So if I was on a desert island and had to do statistics, I would be using the normal distribution because I can work that out without as much work. if I'm using a computer to do it, I'm going to be using the exact test. I'm going to use the exact binomial distribution. And so for that, in R, that would be binom.test. So professionally, that's the one I always use when I'm in this case. All right, so now, when we're talking about 2x2 tables, what we're going to do is that each row will represent population, and each column will be the counts of successes or failures. So each column will be a success and failure column, and this is how we'll organize our data. And so 1, 1 is first row, first column, going from top to bottom, left to right. 1, 2 is first row, second column. 2, 1 is second row, first column, and 2, 2 is the lower right-hand corner of second row, second column. So this entry is the top right entry, first row, second column. This is the lower left entry, second row, first column. And to denote our observed values, we're going to use a capital O and then subscript to indicate where it's located. Now, something that we always want to talk about is like, what are our units when we work through this? And we'll put that off to the side of our table. But so here is a 2x2 table. So here is the case population, the control population. Here is age at first birth. So we have greater than or equal to 30, less than or equal to 29. We're dividing into two groups. Here, first population is OC users, then non-OC users. And then here we have yes and we have no. All right, notice how lopsided the data is on this. All right, so for homogeneity tests, what we're trying to do, we're trying to test whether the proportions are the same in two independent samples. So in homogeneity, what we're trying to do, we're trying to see, is this count proportional to the entry here and proportional to here? So I want for homogeneity, is the entry proportional both to its column sum and its row sum? Is this entry proportional to its column sum and its row sum? Is this entry proportional to its column sum and row sum? Is this entry proportional to its column sum and its row sum? All right, so if all four entries are proportional to their row and column sums, then it doesn't really matter how we chop up the data, because here, when the number that I get for high is high in this row, high in this column, is really, from our point of view, we would conclude has to do with how many I have in each column and each row, not the particular cell itself. Imagine another situation where all of the so if I had 20 entries here and I had 30 entries here, I had 0 and 0, then high and high would be highly correlated. It would be matching up. Normal and normal would be matching up. Or the other situation that I had 30 entries here, I had 20 entries here, 0 and 0. That's the other extreme. There, in that situation, we would see that high would be going to normal and normal would be going to high. And so those are two opposite ends of the extreme. And so what's in the middle is everything being proportional to their row sum and their column sum. All right, so now to solve this, what we can do, we'll just work through, and here's going to be, we're going to take the column sum, and then we're going to take also the column sum of this. Here's our population of 1, population of group 2. Total data size is, is going to be N1 plus N2. And we want to test, do we have the same proportions for each population? All right, so what we're going to do, if we have the same proportions, then this entry would be proportional to this and proportional to that. This entry would be proportional to this and proportional to that, and so on. And so here are those values. So we're going to treat this as the expected value. Now what we're going to do is we're going to take our observed minus our expected value, and we want to get a test statistic from it. So I'm going to take the numbers I observe on my table. I'm going to subtract what theoretically would be there if everything is just kind of, if the table has no additional informative value, what would be there? So I will take the difference in here, and then I'm going to square it, divide by the expected value. For a moment, ignore the 0.5. So I'll take the observed minus expected, square it, divide by the expected value, and then I'm going to add that up. That's going to be approximately a chi-square distribution. Okay, now, why do I have this negative 0.5? Well, once again, that's a correction. So the chi-square distribution is a continuous distribution, but I have discrete values going on here. And so there's kind of a mismatch. So in that mismatch, I want to correct for it by just subtracting 0.5 from these absolute values. And so if I get a test statistic that's far enough to the right, I will reject the null hypothesis in favor of the alternative. The null hypothesis is that we have homogeneity about all the cells in my table. That is to say that every entry is approximately proportional to its row sum and its column sum. And thus, if we fail to reject the null hypothesis, we're saying that really chopping it up in this table manner does not provide additional value informatively. If we reject the null hypothesis in favor of the alternative, we say there's something going on here. There is some connection between these rows and columns. Now, what is that connection? I don't know. I have to go in deeper. I have to look at my data. I need to analyze what's going on. Professionally, when I get into this phase, first thing I do is I look at the residuals. I extract that off of the output from my R code. Look at the residuals, see where it's biggest, see where it's smallest. Specifically, the standardized residuals are usually what I use. And then I start identifying what is going on at particular cells. So contingency tables are a very natural way to present data and present results. So this is a good way to go. Now, something that's going to be important is I'm presenting to you multiple ways to reach similar, nearly the same conclusions. And so a question that's going to come up in real life is, which one do I use for my situation? All right, my advice to you, if you're doing if you're working on an academic paper, look at your journal and see what did previous authors use. Whatever they use is probably the test that you should choose. This will be consistent with the journal overall, and so go with it. Me personally, I usually use the chi-square test because that is well received by a lot of people. That's taught in a lot of programs, a lot of academic programs, for engineering, education, introductory statistics, pharmacy. The chi-square test is presented to a lot of people when they're in school. So when I'm in industry and I'm making a presentation, by choosing the chi-square test, I am choosing a test that my audience will probably be more comfortable with. If they're more comfortable with it, they're more likely to accept my results. That's good for me because I want them thinking about my results, not, oh, I don't recognize this, I don't understand that. All right, so here, this is talking about the correction for the chi-square test. So this is the Yates corrected chi-square test. So this is just another correction to going from discrete data to continuous distribution. Now, one thing that is neat about the 2x2 chi-square test is that the formula is really clean. It ends up being like the determinant squared times n divided by row sums times column sums. you could almost do this in your head during a presentation when someone presents this to you. In fact, there's an academic paper about doing the chi-square test in your head to estimate values. And so this is really easy to get the test statistic, and the expected value is going to be from a chi-square distribution with 1 degree of freedom. So you can just boom, estimate the expected value off of that, or not estimate, the expected value. And so you can eyeball the results pretty easily. Now, Yates Corrections kind of improves upon things from a distribution point of view, and that's just a correction. My advice to you is that if you're doing a 2x2, you probably want to go ahead and let the computer do the work and just automatically do the correction. Unless your supervisor, your editor of your journal, somebody is not comfortable with that, then do it the way that they're comfortable with. Now, Fisher's exact test. What Fisher's exact test does, tackles the same problem, but it handles it differently. Binomial distribution takes 2 populations and converts over to the normal distribution, and then gets a test statistic that way. The chi-square test looks at the difference between observed and expected. Now, this one is a little bit different. Here, what's going on is that in this format, Fisher's exact test considers every single table that could have 7 for the column sum, 53 for the column sum, 25 for the row sum, 35 for the row sum. So it considers every single table where you could get exactly these values. Okay, and from that, what it's going to do is it's going to consider all those tables, and then it's going to compute a distribution of what you should observe, and then you take what you observe, compare it to the distribution from moving things around, and get your p-value. Well, it works out very nicely that this is the hypergeometric distribution in action. And so here, this is how we get our probabilities. This ends up being like super nice, super sweet. This is awesome. And so here, using this, we can do a whole bunch of we can do our computations very easily. Now R will do this very quickly for us. It's easier. In fact, by hand, the presentation of this probability distribution only applies for the 2x2 case. R will handle Fisher's exact test for larger table size, but there's a catch in that the computation time greatly increases if it's greater than a 2x2. All right, so using the hypergeometric distribution, we can get the expected value and the variance, like that. All right, so in the binomial distribution, we simply evaluate the probability of obtaining A successes out of A plus B observations, assuming independence of which subgroup we got from. In the geometric distribution, the outcomes are not independent because once a success occurs, it is less likely that another observation will be a success, as the total number of successes are fixed. So that's something to consider which one you choose. So the hypergeometric does not have independence of consecutive observations. If N is large, the 2 distributions are so close that it doesn't really matter. All right, so my advice on which one to use is consider your audience. If your audience is more comfortable with the more advanced statistics, hypergeometric is a good choice. If your audience is, maybe, they've got some statistics, but not a lot, I would go with the binomial test. For all my cases at work, the results have been so close that it's a matter of choosing what my audience finds palatable over anything else. All right, so here this is just talking about going all over all of the different possible tables that would give you the same row and column sums. Yeah, I'm just gonna skip past all this. All right, so now let's talk about this. So this is leading into Neymar's tests. So concordant data is a matched pair in which the outcome is the same for each member of the pair. Discordant data is a matched pair in which the outcomes differ for the members of the pair. All right, so here what we would do is, let's say I represent my two populations that I'm sampling from as 0 and 1, and I represent success and failure as 0 for failure, 1 for success. If I was to look at that 0 and 1 vector for the population and 0, 1 vector for success failure, concordant, perfectly concordant would mean every time I see a 0, I would see a 0 in the other one. Every time I see a 1 for the one, I would see a 1 for the other. They would be exactly the same. That would be concordant. So in that situation, we would have concordance, perfect concordance, if every time I saw a 0, I would see a 1 on the other one. I would see a 0 and 1, I would see a 0 on the other. Discordant is perfect discordant pairing is that if I see a 0 and 1, I see a 1 in the other. If I see a 1, I see a 0 on the other. So for the pairs. And so the idea of where we're going is that we're going to analyze how many pairs match and how many pairs don't match. And so here, McNemar's test uses exactly that. And so to use McNemar's test, here's our test statistic. It's going to be a chi-square distribution. Now, here's that 1/2 again. This is a correction term. And here's an equivalent calculation. This is the one that I learned in school, by the way. And we can run, we can run our tests as such. Now we can also use the binomial distribution instead of the chi-square distribution. It's probably a better way to do this, but if I have a large sample size, the approximation is going to be so close that it doesn't really matter, and also computation time can be an issue if I force it to be binomial distribution. So here are some p-values, some calculations. All right, so now what we want to do, we want to talk about sample size. All right, so let's say I'm in a situation that I have not collected my data. I want to get an idea of how much data do I need so I can, get the resources, plan out, make sure I have enough time. Well, here, this gives me an estimate of how much I'm going to need. And so I'm going to take the, so delta is going to be the hypothesized difference between the proportions. The P1 is and P2 are the hypothesized values. Here is what it's going to be for the actual value. And we're going to try and figure out the alpha and beta levels for these. And this will be the power of our test. And now if I want to use McNemar's test, here is the values I need if I want to use matched pairs or individuals. Here is the power of the test with those sample size. All right, here is an example of just working this out. of figuring out your sample size before you actually collect your data. I'm going to burn through this. So it's just basically applying the formula that we've already talked about. Now the R by C contingency tables. Now here we're talking about when I have a larger size table than a 2 by 2. In this situation, we're probably going to be using the chi-squared test. And then it's going to, once again, it's going to be observed minus expected squared divided by expected value, add them all up. That will give us our chi-squared test statistic. And then I'll compare that to the chi-squared distribution, and then I'll get my p-value. And then if my test statistic is large, then I will be prone to rejecting the null hypothesis, and we would conclude either I do not have a goodness of fit or I do not have homogeneity, depending on which test I'm doing. So the expected value, if the expected value is derived from being proportional to the rows and proportional to the columns, then I'm testing for homogeneity of counts throughout the entire table. If I have a goodness of fit test, in that situation, my expected value is coming from some hypothesized value that I should be getting for each cell. And so here is our chi-squared test statistic. So for each cell, I take my observed value minus the expected value, square it, divide by the expected value. Usually when we have larger than 2 by 2, we do not have the correction term. And the chi-squared distribution degrees of freedom are going to be the number of rows minus 1 times the number of columns minus 1. All right, so we only want to use this test if no more than 1/5 of the cells have an expected value less than 5, and no cells have an expected value less than 1. If this is the case, I just don't have enough data. What you would do instead is that you would start binning your categorical levels together to get enough data, enough mass everywhere. So if I'm running the homogeneity test and my test statistic is far to the right, I will conclude that I do not have even distribution throughout the entire table. If I'm running the goodness of fit test, there my expected values are coming from some modeled values. And there, if my test statistic is far to the right, I will reject the null hypothesis and conclude that I do not have a goodness of fit, that my observed data does not match my expected value, my model values. Now, in the homogeneity case, which is the one that I usually use at work, from there, the next question is, well, where is the difference when I get a statistically significant difference? Then I look at the residuals, I look at observed minus expected, and I look for the ones that have the largest value. So I'll take these individual terms are added together, observed minus expected squared divided by expected. I look at the value, the cell that has the largest value, I look at that entry first when I want to go deeper after my homogeneity test. And this is basically just saying the same thing in another manner. Now, it is possible if I have 2 rows or 2 columns to apply the binomial distribution to tackle this. Once again, make sure that you have enough data considering your variance to handle this. And the goodness of fit and homogeneity tests are, if you sat down to derive them, you get pretty much the same thing. You'll get exactly the same thing theoretically. All right, so the Kappa statistic, this gives us a reliability measurement. So what we want to know is, if I was to repeat the study, would I get the same thing approximately if I did the whole thing all over again? And the Kappa statistic does that for us. And so what we do is we take the observed probability minus the expected probability divided by 1 minus the expected probability. And then here's our standard error. And so we'll get our test statistic from this, which will be approximately standard normal. And then we use that to get a p-value to reach a conclusion on my hypothesis test. So in summary, we talked about the binomial two-sample test, chi-square test, 2x2 contingency modification from the chi-square test, Fisher's exact test. We talked about McNemar's test for correlated proportions, and we talked about sample size and power to get more power, to get powerful informative tests for us. Well, that's all I've got for you. Take care and goodbye.